So this Schnorr identification scheme was a breakthrough somehow, because there are lots of protocols where you have this bit sending back and forth. So that the challenge is a bit, and you have to react to the bit, and you have these rounds and so on. But if you look at this protocol, then this is really efficient. So because with exponential protocol, you have a constant number of interaction, and you can prove it, at least to an honest verifier, that you know a secret very fast. And you don't need to do these rounds anymore. And so that's something where people can say, okay, what else can we prove? And so we come to the Chalm-Peterson protocol. Now, what's the task here? What do you want to prove? It's that we have two numbers, and they are both to the power of x, but we have different generators, G1 and G2. Well, it could be the same generators, but then it's trivial, because then it's the same number. Okay. But so that's what you want to prove. So what you do is the following, and this looks very same as the Chalm protocol. So we choose a random number R, and we send again two numbers A1 and A2, and both of them are G1 to the power of R. Okay, so this goes to the other side. So we have A1 and we have A2. And verifier receives it, and again, after receiving, sends a challenge C, which is again a number from ZQ. And then we just send back a B. And what we do now is we're doing the Schnorr protocol twice in parallel. So because that's the same number for both of them, we are checking whether A1 is equal to G1 to the B and Y1 to the C, and we're checking whether A2 is equal to G2 to the B and Y2 to the C. So we are proving for both bases that we know the exponent. Yeah, but do we prove that it's the same exponent? That's the question. So let's see. So first of all, this is only computational zero knowledge. Now, if you want to simulate this protocol somehow, and you don't know the exponent, you have to somehow generate A1 and A2 which have the same exponent to G1 and G2. So you can start with R and R, but then you have problems to generate B. So we cannot compute this in a way that we emulate this computation, especially since we now don't know the structure of Y1 and Y2. So that is a problem. Now let's talk about, so completeness follows from protocol. We can convince that this is the case because just follow the protocol. Now for soundness, assume that, now these are two generators, so you can say that G2 is a generator of G1 to the power of H, which is even the case if we choose from GK. So that's something we do in the exercise on Thursday. Okay, now assume that we have two different x and x prime because we want to cheat. So y1 is G1 to the x and y2 is G2 to the x prime, which is different. But we can put this in the same norm. So this is also G1 to the x, h times x prime. So let's try. So the cheating prover chooses two random numbers. Could be different. We don't know. So it doesn't have to be the same. And we get a random challenge. And now we have to compute this B. Yeah, so you have to B. So first of all, we have to compute this B in order to satisfy the first equation. So that's somehow binding us to really compute R minus C times X. Now for A2, what we get is that A2 is G1 to the H times R prime, and G2 to the power of B times Y2 to the power of C is this term here. Now I just put out this H. So what we get is H times R prime. So these exponents have to be the same in order to pass the test. Now I can divide by H because H is not 0, because otherwise this generate would be 1. So what I get is that the cheating prover must choose something like that. So the R prime must be equal to R minus C times X minus X prime, and X minus X prime is now different. So this is not 0. Now we have a following problem that we start with some R, and we want to cheat R prime, and we have to have a certain relationship, which is given by this equation. But we don't know C. So somebody comes and says, okay, I want to cheat. I have two different numbers, but the only way to cheat is if I know what C is in advance. Yeah, so I have to choose R and A prime before I do it, not after it. So I have to fix this, and then C arrives. And C is a random number, so it's probably not the case. So cheat and verifier fails with a probability which is 1 divided by the size of the numbers that we can choose from, which is exponential in the number of digits. So that's the problem. So that's is the proof of soundness. So there is no way to sneak out of it. And what else can we prove? So here what we have done here is we prove that we have to the same. So next thing we could do is, can we prove maybe that I have G to the A and G to the B, and I prove that I have a third number which is G to the A times B. Okay. So now so what I really don't like in these protocols is this sphere. I don't like it because you don't see anything. So we see on the left side, we see A2, but A2 is G2 to the power of R. So that's A2. So that's A2. And then I test whether this is equal to G to the power of G2 to the power of B, which is somehow B minus Cx. So that's what is in the exponent. And then this multiplied with y2. What is y2? So y2 is G2 to the x. So that is y2 to the power of C. Okay, so what I just have done, I just substituted everything into this equation. But why do I do this strange frames around it? That's actually a notation which only I'm doing to understand what zero-knowledge proof is doing. Because this means that you don't know what's going in there. So there is some secret information, and this frame says that you just have this number here, you have this number here, and you have this number here. Yeah? We know what's inside, but the verifier doesn't know it. And so I use this notation in order to get rid of these thousands of variables which do the same thing and try to hide the information. Yeah? So, which gives us two possibilities. If we want to hide this information, when we just black it out like I do here, that's a test what we're doing. But we also know the inside of this. And that's the reason why I do this notation. Okay. I try to convince that it makes sense, but now the next problem is that my presentation program doesn't allow me to use frame boxes for reasons I don't understand. So that's the best approximation I can do in order to make a frame. Maybe I find some other ways to do it. Actually, it's already a pain in the ass to do that in this program, but it's better than in the past. Okay. So this means that the internal structure of A and B is hidden, and we just have this value. We can see that this A times B, but I give it to you and it's hidden. Yeah, so you just see the resulting number. Okay, let's see where things get easier with that. So what we do is, again, we are doing a Schnorr-like proof in this area. So we want to prove that G to the A and G to the B, and then we have G to the A times B. So notice that this is not A plus B. It's not just multiplying them. There's something happening in the exponent. Okay, it's like the Diffie-Hellman scheme that we have seen. We have G to the A to the B. But now the problem is that we cannot send B around or A around. It's not possible to do that. So we do the following. So we choose random numbers R1, R2, and we send some kind of values G to the R1, G to the R2, and then strangely G to the A times R2 and G to the B times R1. So this wouldn't give away any information unless you can build the discrete logarithm. So this is all done to the other side, and you can see on the other side this comes packed now in this nice frame, so he doesn't know what's going on there. Okay, 4 numbers. Interesting. 4 random numbers. So now he sends a challenge here, which is 2 challenges, CA and CB, which have 2 different purposes. Now we send 2 answers. One is R1 plus CA times A and R2 times C times B. So now what we want to do is do the following. This is we have to do 4 checks. So the first thing is, since I go from, I know G is public, I go from G to GA, which is somehow hidden. So this is done by a factor. We know which factor it is. It's a factor A. So this is multiplying by factor A. And on the other hand, I want to show that the same factor gives me from GB to G to the AB. So it's like in the proof of the same exponents that we have seen before, but we want to know that they have the same factors. And the factor here is a factor of A. Same idea as here I have different bases, and you can now substitute G2 with G2 with G1 to the B. It's the same idea that we have here. So again, like here, so you have 1 answer, and I have 2 checks I have to perform, so that this is the case. And this happens here. So here you can see that this is the commitment at the beginning, G to the R1. So this is G to the A, which will be challenged by this challenge A. And then this is the thing that I've constructed in order to fulfill the challenge. Okay. Now we do the same thing with G to the B. We don't know whether it's G to the B at all, but we know that from G to the B to G to the AB, they have the same factor A, because here it's the same exponent. So this is the same exponent I'm using to get from G to the B to G to the AB. This only works if this is the same factor. And let's call this factor A. And we have this term here, which is actually not harm because it's fixed before, and it helps to randomize the thing that we have here, which is G to the B R1. Now the good thing about this notation is that you can verify it's true. Now if I had variables here, I still have to sell the notation here, you don't know what's going on. So what we see is that G to the B R1 is the same thing as here, and G to the B times CA times A is the same thing as here. So it's true, because we can see now into the variable. Okay. So this is the same thing. So we prove that this is the same factor. Now we do the same thing, but symmetry, we prove that I go from G to GB and go from GA to the GAB with the same factor. Again, I prove that this goes with the same factor, which is the same proof again, just by that I start here with g to the b to the power of a challenge, and here I have this random number which is fixed without the challenge, and I get to this point here. And then I do the same exponent for g to the a and get to the g to the ab. So that means I have a triangle. I have g to the ab, I have g to the a, I have g, and I have g to the b. That's not a triangle, it's a square. So what I prove is that this has the same multiplication, and I prove that, so this is the same. Well, maybe I should dot it somehow. So this is the same. And I prove that this is the same. It's like you're multiplying in one direction with the same and the other direction with the same. So it must be that this is g to the ab. Because you're multiplying in one direction with the same factor and the other direction with the same factor, and this is g to the ab is used twice here. So by this parallel proof somehow, you know that you have g to the a times b in the exponent. And you can prove that this is the case without revealing too much information. Again, this is only computational zero knowledge, because you need some hidden knowledge to really produce this thing. Okay, so this is nice because now you can prove multiplication. Can you? And is it really secure? Well, you should be careful, because if you want to prove that g I want to have some secret number g to the a times b, and a is equal to 0, when you can see the result. You have some, or you have small exponents. What you get is g to the a times b, when this will be 1. Yeah. So this holds for all numbers. But what will happen is that if you take some trivial small numbers, then you can see the result. So, but this is somehow bad, because you want to prove maybe that you have 5 euros and the other one has 3 euros. And then you want to prove that now you have 3 times 15 euros or something like that. But 3 and 5 are small numbers. You don't want to prove that you have a very large number of euros. Maybe you want to prove that, but you don't have it. So we want to have secrets which are arbitrary and maybe even 0 or -1 or 5 or something. And this is something you cannot do if you're doing that. So that's the first thing. So how can we commit to such values, and how can we do zero knowledge proofs of that? This is a problem that you have to do. Now, what you can also do, you could adapt the protocol and make a single number and have 3 different generators, G1, G2, and G3, and look at the product. And then you just have to commit to G1 to the A times G2 to the AB and G3 to the AB. And this fixes you that you have to choose A, B, and AB. You can prove that this is the case if you just publish the values afterward. You see the multiplication, it works. And then you can prove that they have the same exponent. And when you're done, and then you have a proof for AB. So you can start building up proofs for that. However, there is a problem here if you do it, because here it sounds very nice and you have a proof for that, because there could be some kind of backdoor which we have to work out. So So let's assume that you just want to have one number and you want to commit to this the same way. Now the thing is, what do we know about G1, G2, and G3? Yeah. So these are just random numbers which are taken to the power of p minus 1 divided by q. This here, 2 to k, 2 times k. But who knows whether I have taken a random number? Now, if I'm giving you the scheme and say these are my 3 generators, it could be that I have chosen G2 as some power of G1 and G3 as some power of H3. So that I have some hidden information in the generators, which I'm now using against you. And if I commit now instead of as commit to this value, then I have as hidden information that this is basically G1 to the power of A plus H times B plus H3 times AB. Okay. Now, if I now want to cheat and say, is it really this number, by just saying this is the product, then I just have to solve this equation for different A and B and see whether I get the same AB. And after some calculations, I can prove that if B and B minus prime not equal to this number, but I choose A prime to be like that, and then I can have the same commitment. So I get the same commitment for different numbers if the product is not is still the same, but I wiggle around with A prime and B prime, and we still make the same product, and it looks fine. But I have not committed to A and I have not committed to B. So I can use the secret information here of these generators in order to sneak out. So what's the solution? Don't know it. Show that you don't know what's going on with G1 and G2 and G3. Yeah. So how do you prove that you don't know something? That you honestly took a random number which has no structure, which we now cannot be distinguished from any other number which has a structure. We are somehow now in our trap of a zero-knowledge proof. We used this lack of structure in order to prove something, but now we can hide information in the generators and we can break the protocol if we want to rely on the lack of information. Okay? Anybody sees the solution? Maybe you see the solution? No? No? Nobody sees the solution. The solution is NUMS, and which is, do you know magicians? Do you like magic shows? No? No? Not so. So what's the first thing what they do? They make a card trick and so on, yeah? So what's the first thing what they do? They take the sleeves up. Nothing in my sleeves. Okay? Yeah? So that's a technique. So nothing up my sleeves. That's sorry, I didn't come up with this name. I would have. So it's a technique in order to prove that the generators are honest. So just reconsider. So we have this prime number here, and we have this large number Q, and this is how you choose the generators. So the idea is we choose a random H. Then we take H to the power of P minus 1 divided by Q, and then we are in this set of GQ. That's the algorithm that we have. Now the problem is, how can we ensure that random is random? Yeah. So we could make this, and it's not random anymore. It still looks random. It cannot be distinguished from any random number. So the solution is very simple. Don't do it randomly. So what we do is we use a random number generator, H, Now we can also take a hash function or something else. And you put into this H the prime number, maybe some seed, and the number for the age that you want to set into this algorithm. So now you have a determined set of generators. You start with the first generator and you publish that. That's how we choose the generators. And this hash function should not be based on set P or set Q. So it should be somehow independent, A, S, or whatever. And with this, you can show that, okay, this is out of this random number generator. I didn't choose it. And I don't know what's the relationship because it's predetermined by that. Which is, by the way, not a problem to choose this randomly. So nobody says that these generators have to be random. They just have to be independent. And there's a very high probability, an extremely high probability that they are independent, and we don't know any structure. So this means if you do it this way, Gi and Gj, this relationship is not known to any of them. And the other thing is you have cheap and numerous generators. Everybody can produce generators and they can all do it the same way. They don't even have to communicate. We just say, this is the algorithm, how we do generators. Please give me generator number 17. And it works. And if you do this, then we don't know, because of a discrete logarithm assumption, the relationship between the generators, and we can store as many information in one commitment as we want. So you can make a commitment of G to the 1, G1 to the 1, G2 to the 0, G3 to 100, G4 to 117, and so on. Just multiply them. And you need only one number, and you commit to all 4 of them. As many as you wish. Because for each of them, the discrete logarithm assumption holds, and it's actually compressed into one number, where if you commit to this number, you have a whole vector of numbers in one number committed, and they're all using different generators, and we don't know the relationship between these generators. So we can compress the communication by a lot. And so this was the first problem that we had. So this problem was that we have this kind of relationship here. So then we can probably do that. The other problem is the choices of A and B, that they're unsecure. And that's something we want to solve as well. And the solution is hidden commitments. Okay, so we want to commit to unsecure exponents like that. So, and this is a problem because if it's a constant choice, the attacker can guess, or maybe you have 3 choices, and even if the choices are complicated but they're known, then you just try out all these possibilities. Now the solution is the following. Instead of committing to G to the A, you commit to H to the R and G to the A. What is H? H is just another generator with no relationship to G, and R is a random number. So to take H to the R, that this will produce a random number. So from all possibilities in GK, you have a random number multiplied with G to the A. Now assume that G to the A is 1. Then you still have a random number. Yeah? So for every choice of A, you have a random number. So your secret is really perfect. Yeah, we actually using this with El-Jamal. In El-Jamal, you have G to the R, and then you have G to the XR times M. Yeah? And here you can even encode 1 with El-Jamal, and it's still safe. You shouldn't encode 0, of course, but that's no way to get the 0 here. So this is the hidden commitment because H is now the hiding generator. It hides the information, and this is the notation that we use. So we have H1, H2, and so on. These are the hiding generators, and G are now the committing generators. Basically, we ignore the information in H. So we don't look at H, what it does, and how it helps. Okay, so that means if we have a set of values E1 to En, we can commit with this term to it. We take h to the r, and r is randomly and stays secret, and then you have some number of exponents. Even if you publish some exponents, it's still safe. Yeah, because the other ones are just multiplications, and everything is now relying on the first exponent, h to the r, which has no meaning. It's just there to hide it. So actually we are sacrificing one generator in order just to hide our information and make perfect space. But we know that it's there, and we know how to reconstruct it, and we know how to prove it. So you can commit to this here, and the commitment will be a random number, a completely random number where the outside side I cannot see any structure. And you can prove that it has a structure, and you don't know what is inside. So you have a whole vector of possibilities where you can prove that this is a vector of n elements, which I don't show to you. Here, have it. Okay, and I can prove that the third value is a product of the first two. I can prove it to you, and you cannot actually learn anything from that because I just used the zero knowledge proof to do it. So that's now open a set of possibilities, because we already identified some ways to prove things. Okay, so what we could do, for example, is we could prove that we have a hidden addition. Let's start with that one. So I have the following hidden commitments. This is one commitment, G to the A. This is the next commitment, G to the B, and it's the third commitment, A plus B. Nobody knows that A plus B is B, and if you do this, you get a random number. So now we will do a zero knowledge proof that A plus B is C. So what we do is, we ask, so this is now all hidden. So we can send this around. So this is hidden. I ask him, oh, you know what? Multiply the first two and divide by the third one. And what we get is, we get h to the power of something, and the g's are gone, if we're not cheating. Yeah? So what we do now is we make a zero knowledge proof that we know the power, that this is a power of h, and we know what's in the exponent. It doesn't matter what's in the exponent. There are three random numbers anyway, but it proves that there is no g. So, or that this is h to the r times g to the 0. That's what we prove here. Yeah? By taking the two commitments, dividing by the third one, and then we get this one. So we can prove that the hidden addition. So for this, we need just one Schnorr back and forth. We can just multiply commitments. So the verifier receives this information, computes this value, and then just follows the Schnorr zero knowledge proof to the base of h. So that's one thing we could do. We could also prove that it's a constant. So we could use that something is a constant, which is even easier. So the constant is known. So I want to prove that this is g to the a. So what I do is, I tell them, the prover asks a verifier, just divide by g to the minus a. And what I get is h to the r, and I just have to prove that h to the r is again h to r. It's very important to make a zero knowledge proof afterward. And you could say, why don't you publish r? I don't publish r because r could be, there could be some calculations before. They have some reasons to hide it. I don't want to publish any things here. I want to keep it secret, and do this by doing a single proof. I only want to publish the things that I want to publish, and here I could publish the value of a and prove it. Can we do multiplications? Yeah. Is it possible to do multiplication with hidden commitments? And the answer is yes. It just needs 2 pages. So let's recall how the multiplication. Multiplication was already not so trivial. So this was the multiplication before. Okay. And this is half of a multiplication after. Let's see what we recognize. And so we commit now to this hidden commitments here. So these are the hidden commitments where we say, okay, we have g to the a, g to the b, and g to the ab, and some factor of h with random numbers. Now you need a bunch of random numbers. I just number them R5, R6, and I think I end up at 9. I'm not sure. And I do the same thing before. I publish g to the R4, g to the b times R4, g to the R5, and g to the a times R5, and so on. And I think I could make this easier by g and g to the b. No, I cannot do this by g to the b and g to the a, because a and b could be a special structure here. So that's something I can't do. Probably I should have. Yeah, I see a mistake here. So probably I have to do this. No, I can do this. These are random numbers. I can publish it. So okay. Never think that you're smarter than the guy who made the slides who was not in the lecture. That's the first thing you'll notice. So I have to trust myself that I thought something about this. So these are random numbers here, g to the 4, and so on. And so these numbers are perfectly hidden. So it's by the discrete logarithm assumption, this is fine, and this is fine, and this is fine, this is fine. Oh, but now I notice a mistake. So here b must be not equal to 1. So this is not fine. So I have to repair this proof in order that a can be equal to 0, which is very easy to do, but I don't do this in the lecture. Now, okay, so I have to repair this slide in order to, because what I have to do is I have to send hidden commitments here as well, because b and a could be 0, and I have to deal with this case later on. Okay, so that's a bummer. So basically that means I have to send here h to the power of some new random number. I have to send h to the power of a random number here, because otherwise I would reveal some secrets. When I have to prove that I need some h to the ri's, and prove that this has this property. And this is done before. Now again, I received 2 challenges. Okay. This is a verifier side. So verifier side will do the same thing. So first of all, I have to prove that this is in the form of GA and h to the power of something. And then I use the same exponent here. Now the trick is the following. So here I have to add some h to the power of some random number here later on. I will repair this for next week. So the trick is the following, that this is the same number, so that I'm using the same factor b here and the same factor b here. Okay, so that's the first thing. The second thing is that all of things are hidden with some hidden factor here, which is just, this h, which we don't really care about the exponents, but we care is that h and g is independent, and I cannot fake g answers with h. So what happens here is, when I do the same thing here, I have already some h here, I will have some h here, I have some h here, and so I will have a very complicated formula here, plus some other term here, which produces this exponent here, which makes sure that this is the same. Okay, the same happens here. So this is the same exponent. Again, we have the same structure. We prove that I go from g to g to the a, and I go from g to the b to g to the ab. And then I prove when I go with a factor from G to the GB and here. And the only complicated thing that's going on here is that I have this additional factors of H, which I have to adapt in such a way that it takes care of all the hidden components, which have to be chosen adequately. So basically, it's the same thing as the multiplication, but now we have to take care of the hidden component and have to choose constants. That is done. And we also add some factors here inside in the equation, R6 and so on, so that we do not learn something from hidden exponents later on. And we prove that these are some new kind of exponents of H. So basically hiding by multiplying some powers of H, proving it with some powers of H, and at the end also adapting so that the equation is still the same. Okay. Now, if you have done this, all of this, is that we can use the following operation. We can choose that a variable is a constant, we can do addition, and we can do multiplication. So these are kind of operations. So if you think as a computer scientist, we have zero knowledge proofs for something like x is equal to 5. Then you have a zero knowledge proof that y is equal to x times c. We have zero knowledge proofs like a is equal to a plus b. No, it's not a plus. Yeah, I can prove of b plus z or something. So we have this kind of statements where you can choose that certain things are equal. Now the question is, so these are called arithmetic operations or arithmetic circuits. So you have numbers and you can do addition, you can do multiplication, you can also do division, you can also divide, and you have constants. The question is, what can we do with that? Can we do everything with that? Or are there certain things which are not possible to do so? So that is the next question. So the question is, but we have to answer, can every function be represented as an arithmetic circuit where we have plus, multiplication, and so on? So, which raises to the audience, what do you think is computable? So, what's the definition of a computable function? So look at your computer. Probably your computer is able to compute a function. How is your computer working? And just open it with a screwdriver and look inside. So what is the basic operation of a computer? Addition. Not how is the addition implemented? So, you have numbers in the computer, how they are stored. Bits. So we're computing bits. And what kind of operations do we have on bits? Okay. Logical operation. So NAND, NOR, XOR, and OR. So that if we can do Boolean algebra, with these operations, then we can do everything because we can put everything into a Boolean circuit. Multiplication, addition, whatever, sorting, everything can be transformed into a Boolean circuit. And now we have operations for these three things. And the question is, can we build a Boolean algebra out of that? For example, can we compute OR with this operation? Or can we compute multiplication with that? So that's the thing that we have to solve. And then if you can do that, we can prove everything with zero knowledge. So that's the goal. So we already have a lot of things for today. So I will stop at this point with this cliffhanger, how to do it. If you look forward in the slides, you can see the answer on the next slide, how to do this. If you want interesting what to do. And the thing is that we not only show that everything is computable, but we show that everything can be proved with a zero knowledge proof with very short zero knowledge proofs, which is quite a new result, which we will show next week when we try to parallelize the addition and multiplication and so on. But for today, I thank you for your attention.